Michael, today you and I are going to put together a hot air balloon. I assume you've never made a hot air balloon.
No, I haven't.
Well, you can make one out of relatively simple things that you find around the house, and it's a nice sort of engineering experience because you have to concentrate on making everything extremely light. First of all, you need struts or stiff pieces, and you can get some of these, can't you?
Yeah, they're straws.
Straws. Have you put two of them together to make them longer?
Yeah.
Okay, you show me how you do that. You pinch the end of one, right?
Yeah.
Okay.
Put
So there you are. You need a total 3 pieces like that, so a total of 6 straws. Then, think you can find that around the house?
Aluminum foil.
Yeah, a piece of aluminum foil. Very thin wire.
I don't know where I'd get that.
Well, a good source is the picture wire that they use to hang pictures with.
Oh, yeah.
It's stranded, so you can just pull out one strand. So you need thin wire, and then transparent tape.
I can get that around the house.
And finally, that.
What is it?
Well, that's solid alcohol. You know where you could get that? It's used underneath chafing dishes and whatnot to melt butter and stuff like that. So anyway, the experiment that we're going to do is one that you shouldn't do by yourself anyway. Your parents ought to help you with it, and they'd have to buy you the source of heat, because to make a hot air balloon, you got to have heat.
Yeah.
Well, here it is all put together. Oh, the one last ingredient is this thing right here. There.
Oh,
a big bag from the cleaners. That's the hot air bag. And down at the bottom here, you see how I put it together?
Oh, yeah.
Here are the 6 straws around here with the transparent tape taping it in place to make a triangle at the bottom, okay? Then here are the thin pieces of wire.
Uh-huh.
And here is the little, that's going to be the
foil.
stove. That's going to be the stove. Then I've attached a piece of string to it and the cup at the other end as an anchor because I didn't want to go too hot.
Yeah.
That's not part of the balloon. So come on around over here. Here, come on over here. And you hold the balloon up like that. And I'll get the solid aluminum or solid alcohol and put it here in the dish and then light it. So you hold it up so that we don't get the heat next to the thin plastic because it would melt otherwise. Okay, are you ready?
Yep.
Here goes the fuel. You sort of spread it out to make a nice hot flame with the minimum amount of fuel. And now you light it. And if all goes well, we should launch our hot air balloon. Hang on to it, don't let go. Getting filled up?
Yeah, it's full.
Full of hot air. Now, why does this work, do you know? Why is it going to fly, hopefully?
Well, because of the hot air that's inside, and hot air is lighter than regular air.
Regular air.
So
and
it rises.
therefore, cold air is going to push it up. So doesn't it seem strange? Gravity ought to pull down on the balloon.
Yeah.
And yet it's going up because the hot air inside weighs less than an equal amount of cold air, so the cold air, in effect, pushes up like a bubble.
Oh, I see.
Like a bubble in water. There we are. That's how to make a hot air balloon out of a clothing bag. This is a powder that sort of floats on top of the water, so we can see what's happening at the top surface.
Okay.
But that's not what the experiment that we're going to do. We are going to put drops of this glue on the water. Put 1 drop right there once.
Okay. What? It's moving.
See, it looks like it's alive.
Yeah.
Put a couple more.
Okay. Ooh,
there's
looks
a
like a
snake.
snake.
Yes.
Why did it do that?
Well, in the glue is a chemical that breaks the surface tension of the water. You know, there's a little sort of skin on the top surface of the water. Well, in the glue, in order to make sure that it wets the surface, they put that chemical. And of course, when you put it on water, part of the surface tension on one side is broken more than on the other. So that's why it starts to move. So go ahead, put a whole lot of them. In fact, I'll put some on toothpicks, and they become little glue-powered boats.
Neat. Make a long stick.
So when you're ready to dump out the water in your little wading pool, why just throw a couple of toothpicks with airplane cement or some kinds of glue on it and sprinkle it on the top. You can see all kinds of mysterious looking wild creatures due to the breaking of the surface tension. This is what is left of a flower that's been under your nose many times. The parts you can see here are the anthers and the sepals. The other parts have grown into a fruit that's so heavy it hangs upside down on the tree. When you find the withered flower, you'll be looking at what is really the top of an apple that started out as a bud that blossomed into a white flower. The tube part of the flower, below the petals, expanded as the seeds developed and became the fleshy part of the apple you eat. Next time you get ready to bite into one, look for what's left of the withered flower at the top of an apple. Jason, you're quite familiar with the number system called decimals, right?
Yeah.
You use it all the time. And here's a typical number in decimal. What does the 4 stand for?
4 ones.
And the 7?
7 tens.
Right. And the 3?
300.
Right. So it's a very quick method of writing fairly high numbers. Well, as you know, the computer can't read decimal numbers like that. You've heard about what it uses?
Yeah, it uses something called binary.
Right. That means that there's only 2 positions of a switch, either on or off. That's why it's binary.
Yeah.
And here are the switches.
Okay.
That's a switch for 1, for 2, for 4, for 8, and 16. Down here I put the decimal numbers.
Okay.
So 0, no switches on at all.
Right.
Now, if you want to turn on this switch, that would stand for
1.
For 1. Can you turn on the switch for 2?
Sure.
Okay.
Like that?
Now turn on the switch for 3.
For 3, there is no 3.
No, but you could turn on.
Oh, I can turn on 1 and 2.
Right. Now 4 should be easy.
Yeah.
Just turn on the next switch, right?
Right.
5.
Well, 4 and 1.
And 6.
4 and 2.
2. 7.
1 and 2 is 3, plus 4 is 2.
Okay, now you can see why they jumped from 4 to 8.
Yeah.
Because you filled up all this row, right?
Mm-hmm.
So 8 is simple. Turn on 1 switch.
Like that.
Okay, now 9. Whoops, wait a bit. Yeah, okay.
And
very good, 9 and 1.
1.
And so on. And then you'd repeat this. And as soon as you ran into number 15, you'd put one checker on for 16. And
right.
Off you'd go. Now, the question that I often have wondered is why do they use such a cumbersome system? Look at all these switches they have to turn on and off when the decimal system is so much easier.
Yeah.
The reason why they do is because even though it's a rather cumbersome system, the computer can do it very, very fast.
Oh.
Very, very fast indeed. In fact, I have them set up on the computer. Come over here and take a look at the rest of the binary numbers. You got up to what, 9?
Yeah.
Okay, push the down arrow and the repeat over there, and you can run through a whole bunch of them.
Okay, so that's...
It's already at 16, right, down at the bottom?
Wow.
There they go.
There they go.
Yeah.
You can see how the switches.
Yeah, hit. Okay, repeat and keep going.
Okay. Wow.
There you go.
Yeah, you can
78.
You can
Keep going now.
You can see how
89. You see the pattern develop?
Yeah.
You see, obviously, this one comes up. Oh, there's a new one.
Yeah. Oh, there's a
128.
new row.
You're right. The new 128. So it's going through those relatively quickly.
Yeah.
But the other thing that I wanted to show you is how fast it can read them. Okay, stop for a minute.
Okay.
Do a Control U.
Okay.
And then G. Now we're going to find a number. And See, there's 497 up there.
Yeah.
Okay, if you push escape, watch how fast it goes through those to find 497. Go ahead.
Okay.
Page 2,
yeah,
page
is
3,
that
4,
going
5,
fast?
6, 7, 8, page 9. There it is. See it?
There it is.
And
right
there's
at
the
top.
binary representation of 497. Obviously, it's a 1, and then 16, 32, and so forth and so on. Anyway, I just thought you'd kind of like to be introduced to the binary, even though when you work with computers, you don't pay any attention to it at all because it's the language of the computers. But you ought to know at least that this is what it's handling. Every time you type something, even the letter A, it's changed first into a decimal, and that decimal is changed into binary numbers like that for use by the computer. You know how much air goes in and out when you breathe?
No.
Most people don't. Now take a deep breath. What's going on inside of you when you take a deep breath, you know?
Well, my lungs are inflating.
Yeah, and then when you let the air out?
They're deflating.
Well, that's sort of true, but there's a lot more to it than that. In fact, here, I have a model of your lungs right here. See, it's a lamp chimney with a one-hole stopper in the top there, and a Y made of glass and 2 balloons. Down below is another balloon that represents what?
My diaphragm?
Your diaphragm, that's right. Okay, so grab a hold of your diaphragm and make it go up and down slowly. Okay, now it's down. Now what happens to your lungs?
Well, they're inflating.
Yes, now what? Move the diaphragm up.
Oh, they're deflating
Yes,
now.
now diaphragm up and down. There's
Breathing.
Michael breathing. All right. Now notice that you said your lungs inflated and then deflated, and that's true, but it's really the diaphragm that's making it do it, and outside air pressure is pushing it and making your lungs fill up. You make more room inside there when you inhale like that, and then the diaphragm pushes up and forces all the air out again. So that's how your lungs work. Okay, good. Now, I want you to take the deepest breath you can and then exhale as much air as you can.
Okay.
Okay, now how much air did you take in and how much air could you possibly blow out? Come on over here. Here are 9 one-pint jars. What was the maximum amount of air that you could exhale?
Well, 1, 2, 3, 4, 5.
5 pints. Okay? Well, now we're going to actually see how much you can exhale. Over here, see, I have a great big tube filled with water. And see those black marks along there?
Yeah.
Each one of those black marks represents a pint. So you said how much?
1, 2, 3, 4, 5. That's how much I have to blow?
Well, you don't have to blow that much. That was your guess. Think you can do it now that you see how much space 5 pints is? Well, why don't you try it? Let's see. Around on the other side over there, at the bottom of this tube, there's a hole. See, and there's a rubber stopper in it?
Yeah.
Take the rubber stopper out.
But won't the water come rushing out?
Try it.
It didn't come out.
Okay, why not?
Well, there's no air in there, so the water can't come out.
Right. And the only air that's going to get in there is the air that you blow.
Yeah.
And here's how you're going to do it. See this tube? Stick it in the hole.
Okay.
So all the way to the other side of the tube. Okay, that's great. Now, on the other end of the tube is this plastic one. And you are going to blow. Practice once, the deepest breath you can, and then as much out as you can.
Okay.
All right, go. Okay, come around here and take a look. How'd you do?
I only got
3
3.
and a half. 3. I want to put this little piece of tape here. I'll mark that. That's the top of where you were that time. 3. That's pretty good. Think you want to try it again? Think you can do better than 3 1/4? Try it once more. Okay, you ready? Take a nice practice now. I find myself too. Go ahead. Here we go. Okay. Come on around, take a look at it.
Oh, I did a little better.
Just a little better. You know, you were from the top up here down to there. You did a little better. Yes. So that was a pretty good guess, because after all, you didn't really have any experience at how much air you breathe in and out all the time anyway, did you?
No.
Well, let me see if I can sort of summarize it all for you. Now, the figures I'm going to give you are for an adult, but the proportions would probably stay the same for a boy your size, so you'll just have to cut part of it off, okay?
Okay.
First of all, when you breathe in and out, that's how much air goes in and out.
1 pint?
1 pint. Normal breathing. Then when you take the deepest breath that you possibly can...
3 pints?
3 pints, right. Then if you just let it all out, obviously you're letting out 4 pints, right?
Right.
But if you take the deepest breath you possibly can and then exhale everything that you possibly can, like you just did, normally an adult...
3 pints.
3 pints. So there is sort of the maximum amount of air that you can put in and out of your lungs, because these 2 pints over there are in your lungs even when you breathe out as much as you possibly can.
I see.
So all those little tiny, have you ever seen what the inside of a lungs looks like?
No.
Full of all tiny little air passages. And inside those air passages is at least 2 pints of air. Now, do you know how you can improve your ability to breathe and exchange air, the oxygen, into your lungs and so forth?
No.
Deep breathing exercises. Very good for you. Practice now. Here we go. You've seen products torture tested, but nothing like what this container goes through. It's slammed into armor-plated concrete. It's crushed with a hydraulic press. It's punctured with a steel spike. It's slashed by a metal I-beam. It's burned in a roaring fire and finally held underwater for 8 hours. Yet after going through all that, the contents are unharmed. What's all the testing about? Well, they're designed to test a portable container for plutonium, one of the deadliest poisons. Plutonium is a waste product of certain type of nuclear reactors. To make sure it's not secretly being used to make bombs, nations send samples by airplane to laboratories for analysis. So a few ounces of plutonium must be protected in a container that can withstand the worst possible accident. Scientists and engineers at Sandia National Laboratories went to work on the problem. The container they developed is really a series of containers, one inside the other to absorb the force of any kind of blow. In a test with radioactive material, none of the tortures produced even the slightest leak. So plutonium samples that have to be analyzed as part of international nuclear treaties can be shipped safely because a small super container was designed and developed by scientists and engineers to withstand the world's toughest torture tests. Stacy, here's a small glass and a spoon. I would like you to get the spoon into the glass without touching the spoon.
Okay. No, I can't
Nope.
do that, right? Let me try just once more. No, it won't stay in.
Now, the secret is that the spoon is a lever. You've studied levers in school?
Yes, we have a bit.
Ordinarily, it's a lever in which the fulcrum, or the pivot point, is back here. You apply a little force here to get a lot of movement out here.
Okay.
That's the way you normally use it. But the spoon can also be a lever in another way. If you push down here...
The end will come up.
Yes. Here's where you apply the force. There's where the pivot point is, and here's where you now get a lot of motion.
Okay.
That's how you get the spoon into the glass. I didn't say that you couldn't use another spoon. What if you did it like this? Go around over there at the end.
All right.
You set the glass about like that. You take this spoon and you put it under here like that.
Oh, I see. And you hit this
You
end.
hit that one, and if you do it right, it should flop right into the glass.
Okay.
Just like that. So try that on some of your friends.
Okay.
Using the spoon as a new kind of lever.
Okay, we try it again.
Very good. Tanis, we're supporting, let's say the book weighs 1 kilogram.
Okay.
How much force are you exerting on your side?
Half a kilogram.
And I'm exerting half a kilogram on my side.
Mm-hmm.
Have you ever noticed that suspension bridges always sag like that?
Yeah, they always have a curve.
Have you ever had clothes on a clothesline? The clothesline always sags like this. Or a chain between two posts, never goes straight across, always sags. Well, that's based on a very important scientific idea called vectors. Have you ever heard of vectors?
No.
Well, scientists diagram forces by the length of the arrow and the way it points. That is a sort of indication of how much force is applied. Hold your end again. In this case, when we pick it up like this, half a kilogram on each side, assume, there'd be an arrow that goes up like this. An arrow going down like this for the book, and an arrow going like this for the fact that it's suspended.
Okay.
But now as we start to move the two supports apart, that vector still has to be 2 pounds over here, but we're now applying it at a great angle, aren't we? Mm-hmm. Right. And the more we apply it at a great angle, the less force there's going to be there. Hold it nice and level now. Okay, pull. Get it straight. All the way. I'm pulling you. We still haven't got it straight.
No.
Let's do that again. This time with some sort of a scale in the middle so that we can see. Here, you hold that rubber band, and I'll hold this one. Now the rubber band on each end is going to sort of represent the amount of force we're applying.
Oh, okay.
The more it stretches, obviously, the more force.
Right.
Okay, let's do that again. Can you hold it up a little higher so it's off the table? Okay, you can let go of your other hand there. Okay, now pull. See what happens to the rubber bands?
Yeah, it's stretching quite a bit.
Stretching like crazy, and we're putting a great deal of force here, but obviously not enough to counteract 1 kilogram in the middle. We could go like that, and eventually we'd break the rubber bands.
Yeah.
And that's why suspension bridges are always sagged like that, because if you tried to make them go straight across, they'd probably put enough force on it to actually break the steel.
Oh.
Yeah.